Our project is based on the article Modeling the Dynamics of Smallpox Outbreaks in London by S.R. Duncan and C.J. Duncan. The study discusses the evolution of smallpox outbreaks from 1647 to 1893 using a standard susceptible infected recovered model. Duncan and Duncan also used the bills of mortality for the recorded deaths due to the disease. Because of the SIR model, Duncan and Duncan concluded that the smallpox endemic was increased by external forces, which increased the amplitude of the outbreaks. Due to the smallpox vaccine, the endemic levels declined and the periods between outbreaks lengthened. The article focuses on the variations in the force of infection, showing that outside influences were a key factor in the variability of the disease.
The article begins by defining a simple SIR model of the disease that uses three coupled differential equations shown here. The three equations model and show the rate of smallpox transmission between the three classes of population, including X, the number of susceptibles, Y, the number of infectives, and Z, the number of immunes. The total population, represented by N, can be modeled like so. The force of infection, represented by beta of T, is modeled by sinusoidal oscillations around a mean level of beta 0. This then gives us these new equations with x0, y0, and n0 denoting the solution of the differential equations when beta of t equals beta 0. Plugging this back into equations 1, 2, and 3 yields these equations. For the purposes of our analysis, however, we focus on the model when the variations of force of infection are small. Thus, we assume beta t is constant. This gives us these new equations and the characteristic equation with these substitutions for resonance frequency, omega r, natural frequency, omega n, and the dampening factor, gamma. This leads us to Figure 1, which shows two models of smallpox deaths over time, including the nonlinear oscillatory model, represented by the solid line, and the linearized model where the force of infection is constant due to endemic levels of smallpox, represented by the dotted line. The force of infection, represented by beta t, varies sinusoidally with a period of 2 years, causing the oscillations between high and low deaths of smallpox.
To reproduce a portion of the model, we focused on testing the author's claim that there are three roots in their model. They claimed that there are a pair of complex conjugate roots in the left half plane, indicating the system has a resonance frequency causing the force of infection to oscillate, and an unstable real root close to the origin indicating a relatively slow increase in the population over time. These three eigenvalues indicate the model has a spiral saddle point. We began by attempting to solve the system analytically. When no analytical solutions could be found, we used technology to approximate solutions to the system numerically by inserting the parameters given in the article. We chose appropriate population parameters that reflected the original model and found that the system does have three eigenvalues. These eigenvalues indicate there are a complex pair of conjugate roots in the left half plane and a positive real root close to the origin. This confirms the author's claims and models the endemic behavior appropriately for the times when the force of infection is small. To show how the equilibrium point changes with various initial conditions, we plotted the eigenvalues on the real and imaginary axis. Here we see two complex conjugate roots on the left half plane and the real positive root near the origin for the initial values susceptibles equals infectives equals 10. This equilibrium point is classified as a spiral saddle point with index 1. Keeping the initial number of susceptibles and infectives equal, we clearly see a bifurcation occurring between 3 and 4, where a saddle point, two opposite real roots, changes to the spiral saddle point seen previously. Here we plotted the model for varying non-equal initial conditions. The green plots show the bifurcation that occurs when infectives are kept constant at 3 and susceptibles increase from 4 to 5. The blue plots show the bifurcation that occurs when susceptibles are kept constant and at 3 and infectives increase from 4 to 5. Both of these bifurcations are saddle points with index 1, changing to spiral saddle points with index 1. Here we have an animation showing the bifurcation occurring as the infectives increase. It occurs between 4.26 and 4.27 as the saddle point with index 1 changes to the spiral saddle point with index 1.